Hello everyone, this is Levi Sheridan. Today I'm making a video about an autonomous combat robot that I built for an autonomous mobile robots course at school. This is Dr. Bones. He was designed and built to compete against one other robot in a 10 by 6 foot arena. On either side of the arena, there are the robot's home bases where they start each match. In between the home bases, there are various obstacles intended on making navigating the arena difficult. Each robot and their home base was required to be equipped with an array of IR LEDs. This is required so that each robot is able to locate and track their opponent and the opponent's home base. Each robot is also allowed to carry one ping pong ball at a time, which is used as a projectile. The objective of each robot is to navigate into the field, to avoid obstacles, to locate and track either of the two targets, being the opponent or their opponent home base, and then to fire the projectile at the opponent or the opponent home base, at which point the robot must turn around, return back to the home base, at which point it then can be reloaded and sent back out into the field. Points are awarded for hitting one of the two targets and are deducted for bumping into any of the obstacles, to the walls, or for getting stuck in the field and needing to be manually located back to the home base. Dr. Bones performed incredibly well. He actually won the competition and was the best robot in the last 5 to 6 years, and I'm really happy with how it performed and a lot of the different features and how well it all worked together. So in this video, I'm just gonna kind of give a general overview of Dr. Bones. We're gonna go through all the individual features, the outside, the inside, how it was made, and some of the things I'm really happy about, and maybe some of the things that I think could have made it better. So getting straight into it, Dr. Bones is equipped with a Mecanum wheel drive train. This is really advantageous for such a competition because it makes Dr. Bones super maneuverable. Each one of these motors is individually powered with a brushed DC motor, a geared brushed DC motor that you'll see inside when I open up Dr. Bones. But this specific drivetrain is super advantageous because Dr. Bones is actually quite large relative to the arena, and this allows him to be really agile and navigable through the arena. This Mecanum drivetrain allows Dr. Bones to not only translate back and forward like a traditional drivetrain does, but also horizontally without turning, or really at any theta angle that you can define. So it makes Dr. Bones really great at navigating around the obstacles and then also while keeping an eye on the target and the opponent. The method that we used for obstacle avoidance and obstacle detection is an RP1 LiDAR. This is a 360-degree LiDAR sensor. And this basically gives us distance readings all around Dr. Bones, which allows us to figure out what's close to us and what's far away, where we're able to drive and where we're not able to drive. If we had more time, we could have implemented something like SLAM for localization and maneuvering, where we actually map the arena, but we did not do this. We used it strictly as a really capable and powerful distance sensor for all the way around Dr. Bones. Like I mentioned, we had to carry that the IR beacon with us, and that had to be at the top of the robot. So we had to include these standoffs that allowed us to place this above the LiDAR sensor. And basically in software, we just cut this out of the view, these two standoffs, and it worked quite well. So that is how we did obstacle avoidance and detection. How we did target detection was different. We used actually a very specially modified camera located right here on the front. Behind this film, there is a ArduCam night vision camera with the IR cutoff filter removed. This was basically to allow us to have high sensitivity to IR light. However, we found that the lights in the room also generated a lot of IR light, and so did the natural daylight from outside the window. So what we did is we included this polarized film. There's actually 2 sets of 90-degree polarized film, so 4 pieces of film in total in front of the camera lens in the outside world, and this worked incredibly well. I'm going to put a photo on the screen of what the robot actually sees when it looks at the opponent, and basically the way that we used this data was to basically center the brightest pixel in the frame, within the frame, and then that way we knew the opponent was directly in front of us. We then had a conditional statement for the distance provided by the LiDAR sensor to then to trigger the firing mechanism of the cannon, which is located here, and I'll talk about that briefly. But these two together were used to create the conditional statements necessary to fire. And this worked super well. It's a super simple system. Basically, if the brightest pixel is on the left of the robot just turns a little bit to the left until it's to the center. And we had kind of a range that we defined in testing and found worked really well. And it was a really great system, really well performed. And I'm really happy with the camera. It's super compact and worked really well. For the projectile, we used a spring-powered cannon. I'm going to talk a little bit about this more when I open up the robot, but I'm really happy and very proud of this cannon. I set out to make it super powerful. We had no constraints. We could have used compressed gas or even propane, but I went with a spring-powered system just for simplicity, and I used a stacked wave spring. I'm going to get into this more later, but it worked really well. I was shooting for 15 to 20 meter per second barrel velocity, and I actually hit that target, and it worked super well. Again, we'll talk about it more briefly once we get to the inside. Dr. Bones on the left side of the cannon is also equipped with a speaker system to play intimidating music during the matches, and I think that's what kind of pushed us over the edge and allowed us to win. On the back, it's much more simple. We have a battery compartment here, and I'll open that very briefly just so you can see that. Nothing super fancy, and there's just a nice motivation, or I guess not motivation, but words of wisdom on that door. Don't panic, with some nice thumb screws. And then on the inside, we have our battery, our main battery. Dr. Bones is actually powered with two batteries, one for the motors and one for the sensors and the camera and the Raspberry Pi that powers everything on the inside. So now I'm going to open up Dr. Bones so we can see inside of him. I think he looks really nice inside as well as out, so we'll get into it and I'll show you everything. I'm a big fan of cable management, so I tried to do that. Also made a bunch of custom cables that I'll show you briefly, but kind of just starting in the front to the back. We have the camera module here. This is fully enclosed, and that was necessary because the camera is really sensitive to the daylight. So I had to make sure it was super well sealed. This is a 3D printed enclosure. I'll maybe throw a photo of like the cat or something on the screen so you just can see it, but it's super easy to remove actually. Just these two screws, countersunk screws that's flush with the front, and this whole module just kind of pops out. It's a USB camera. It's an Ardu cam, works super well, really compact, fits really well in this arrangement. To the left, we have the Canon, so I'm going to spend a little bit more time and talk about the Canon. This is a fully 3D printed, and it uses basically, like I said, a stacked wave spring to store their energy. And I use the stacked wave spring because it's super energy dense compared to a standard coiled spring. I could put up the specifications for my spring on the screen. I got it from McMaster-Carr, but I believe just off the top of my head, it's about 0.8 inches of compression, gives us about 30 pounds of force, which is just like crazy. And again, I'll put like a cross section so you can see how it's working. But basically we have our spring inside, and then there's a plunger that compresses the spring. And connected to the center of the plunger, held on with that screw, is a linear rod, I believe an 8mm linear rod. And then inside of this 3D printed compartment here, there is a linear bearing. So the plunger just kind of is able to very easily, it's constrained to only this translational distance here, and then when we compress the spring, the rod goes through the bearing, the spring is compressed, and then you can see there kind of like there are these little ledges on either side that's connected to the plunger. So when the plunger is depressed, these servos then are rotated to catch those lips on either side of the plunger, and that keeps the spring retained. Once we're ready to fire, we just simply rotate the two servos, one on either side, and that releases the spring and very quickly shoots the ball out. One of the things I found in testing was that actually the initial release of energy of the spring, if the ball was sitting directly on the plunger in the compressed state, was that the ball would be kicked out and it wouldn't really follow the travel of the plunger. So what I did is I placed the ball towards the front of the barrel, and then the spring basically just contacts the ball at the very last second of its travel where it has the greatest velocity. And I found that worked really well in testing. I was able to achieve the 15 to 20 meters per second muzzle velocity, and this actually worked so well. I felt quite bad, but during one of the matches, our cannon fired and it broke one of the wheels of our robot, of the opponent's robot, because it was so powerful. And I'll put a video of that, but thankfully they were able to fix it and continue competing. So that's the cannon. I put a lot of effort into the cannon, going through all of these different iterations, not only just like the physical design, but like the retention mechanism. That I started with some solenoids here that were really weak, and then I kind of just started sizing up the solenoids, and those still didn't work. So then I tried some different servos, and I'll make a whole nother video about this hopefully soon. But this was one of my favorite parts of the project, the cannon, because it just like took so many design iterations, and then it finally worked one day, and it was really exciting, and it worked really well. And I'll put some videos again of that up on the screen, like on the side or something, and definitely at the end, so you can see that working. But I'm definitely gonna make another video about that. On the left side of the cannon, we have our speaker, again, just kind of for fun. Then in the middle, we have our LiDAR. I kind of set everything that needs to be set about the LiDAR. Just it had to be mounted at the top to avoid seeing any parts of the robot, but also below the beacon, so we had to create the standoff system, but it worked really well. I think if we had more time, we could introduce some SLAM and maybe a little bit more of a complicated control scheme, but it worked quite well, just kind of seeing what was around us and avoiding the closest objects. In the back, we have our Raspberry Pi. This was the brains of the operation. It can process all of the data from the LiDAR and from the camera and sent all of the commands to our 4 motors here that we have that I mentioned before. These are brushed DC motors with gearboxes, 12 volts, 40 RPM. And they worked quite well. They're fairly inexpensive motors. They did come with encoders, and I made these nice custom cables that I talked about for those encoders as well, but we ended up running out of time and not being able to use the encoders, and it would have been much better if we could. I think that was probably like the next step, if we had a little bit more time, was to get the encoders working. It would have been really great. And then also improvements in the LiDAR, but it was what it was and obviously worked out fine. But yeah, we have our 4 motors for each wheel, obviously, and then each motor on the 2 motors on each side are powered by one motor driver, one on each side, and then they're connected together for power, and then jump back to the Raspberry Pi for the signals. And those worked really well, and those are powered directly from the battery that sits below the Raspberry Pi and the LiDAR in the battery compartment that I mentioned earlier. But that's pretty much the whole robot. I made these nice custom cables. Like I said, I'm a fan of cable management, so I try to do my best and I try to make it look nice, but that's pretty much it. Again, Dr.Bones mostly 3D printed components, like the front and back panels are 3D printed, the wheel wells are 3D printed, the top cover is acrylic, and the side panels and the inner side panels are also acrylic, and then the bottom's acrylic, but a good mix of 3D printed and acrylic parts. I think it looks really great. It worked really well. I think it looks really nice once it's all sealed up, and of course it worked well, and I'll put some videos of that, but that's it for now. I hope you enjoy the videos of the competition. I'm really happy with Dr.Bones. I think it turned out really great. So thank you so much for watching, and keep an eye out for the video about the ping pong ball launcher. But thanks again, and have a great day.